Okay, so when we talk about calorimetry, we're talking about connecting how much heat is going into or out of an object with the change in temperature of that object. Okay, so we're going to be using in our examples a couple of imaginary blocks. One's a copper block and one's an aluminum block. You can see there the copper block's at 400K to begin with, and the aluminum's at 200K to begin with. The other details are in there, the mass and the that happens to have the size in there. Okay. Now, what you need to be sure you got your head around is the difference between temperature and heat. Okay. Temperature is sort of an arbitrary number that relates to how much molecular motion we have within the object. And then heat is the transfer of this random kinetic energy from one object into another object. Okay. And that can happen in different ways. So we've got conduction, radiation, and convection. And I'm not going to go into that here, okay, because that's in the soft chalk lessons back in heat and temperature stuff. So make sure you know that, okay. Easy points on the test if you got your head around that. So let's say the copper block is going to cool off somehow. We don't know how it's cooling off, but we know it is cooling off somehow. It's going to move from 400K down to 350. All right. And we want to figure out, so how much heat had to go away from the block, how much heat had to be extracted from it, or how much heat did it have to give off? Somehow it unloaded some heat and its temperature dropped as a result of that. Okay, so we're just going to use our equation here. This is often called MCAT, okay, because it looks like MCAT, you know. So let's see here. We're going to Q out, and that's going to be the mass of the copper, the specific heat of the copper block, and the temperature change of the copper block. Now, when you're doing that temperature change, it needs to be like we had with the thermal expansion. It needs to be in Kelvin units. Okay, you can also do Celsius because a Celsius chunk and a Kelvin chunk are the same size. Okay, that way. So you could do Celsius, but here we go. We've got 250 for our mass, and that's grams. Okay, and we want to make sure we put our units on here. So then we got 0.386 joules per gram Kelvin. Okay, and then our delta T is, our final temperature is 350. Our initial temperature was 400. Okay, and those are kelvins, by the way. Okay, like that. So it's going to be a negative 30 is what it is overall. Let's check out our units. Okay, our grams cancel our grams here. Our kelvins are going to cancel over here. And so we're left with joules as our unit of heat energy there. All right. Now, most of what we've done so far up to this point, whenever we've considered mass, has been in kilograms. And so you probably have a good habit of converting anything you see in grams right into kilograms. Pause that reflex for this kind of thing. You need to be in grams, okay? And the reasons for that are historic, and we don't need to go into them, and they don't really matter. But nonetheless, make sure you're in grams when you do this kind of thing, okay? Because these values for these coefficients are always listed this way, okay? Anyway, we do our math on this thing, 250 times 0.386 times negative 50. And what we're going to end up getting is minus 48.25 joules. Okay, just like that. So that's what we had to pull out of this thing. So we would say we took 48.25 joules out of there. Okay. All right. Now, in the next example, what we're going to do, we're going to take the same amount of heat, the 48.25, and we're going to dump that into the block of aluminum. All right. And then we want to try and figure out what is the final temperature of the aluminum when we do that. Okay. So what we're going to do is the same thing. Start with the exact same equation and work with it from there. Okay. This time, though, let's write Q in. And so we've got mass of the aluminum, Ca for the aluminum, delta T for the aluminum, okay? Now, I want to expand my delta TA because I don't know what it is. In the last example, we had numbers, and so we knew exactly what it was. Here, it's one of the things we're really solving for. So this is going to look like MACA T final minus T initial. Okay. All right, so we're going to have a little bit more algebra on this one. Okay, so we're going to have QN, all right, is MACA T final minus MACA T initial. Okay, now I'm going to skip a little bit of algebra here, but if I was solve for TF, I would take the TF and the MACA over to the right-hand side. Then I would divide out by MACA, and what I'm going to end up getting here is that TF is equal to QN over MACA. All right, and then I'm going to have plus TI whenever I do that. That looks like a 7. Let me fix that up there. See if we can make it look a little more like a T. Hey, there's a nice T for us. Okay, so T sub I. Now I'm ready to plug in my numbers. All right. So if we do that, we're going to end up with QI is 4825 joules divided by 100 grams and 0.9 joules per gram Kelvin. And then plus TI, which is 200 Kelvin. Okay. Now let's check out what happens with our units. Here I've got grams, cancels grams in my denominator. I've got joules here and joules there that are going to cancel. So what I'm left with in this term is Kelvin. So that works out pretty well. Those things match the way we would hope they would. And when I go through the math on that thing, what I'm going to get is, what am I going to get? Oh, I forgot to write it down. I think it's like 304, something like that. Okay, I'm going to have to calculate that real quick. So I'm going to pause it and run the numbers myself. Okay, yeah, it's actually 253 is what that number is. Maybe rounds up to 254. Depends on how many digits you want to try and keep track of. Okay, so anyway, and of course that's Kelvin. Okay, now let's kind of graph what happens to the temperature of the two blocks as a function of time. And what we're going to see is that the copper block is going to cool off over time like this, while the aluminum block is going to warm up over time. Now, if we put them both in the same isolated container where we've got it like in a piece of styrofoam or something like that, like a styrofoam cooler, that kind of thing, then what happens is they're going to come to equilibrium at some point. And they're going to end up being the same temperature, all right? And that temperature is going to be the equilibrium temperature, just like that. And so what we want to be able to do is to say, given two masses at two temperatures, what is their equilibrium temperature once that happens, okay? So that's what we're going to do here, okay? So I've got my copper block, and it's going to give up heat to the aluminum block, all right? And it starts at 400. The aluminum starts at 200, and they're going to meet somewhere in the middle, all right? So I'm going to put over here that we're looking for some final temperature of the copper, and that's going to be the same final temperature for the aluminum, okay? All right, now I'm going to try to do all of this, okay? And I'm going to need a fresh screen here, nice big blank screen. Now our starting point for when we do this is going to be thinking about the amount of heat, okay? So the copper is going to lose some heat, and that's going to go to the aluminum. Now, when the copper loses heat, that's actually going to be a negative number. But when we put that into the aluminum block, it needs to be positive. And so what we'll do is we'll put a minus sign in there just like that to flip that thing around and make it positive the way we need it to be. So let's put our MCAT in here. Okay, gonna get busy. So MC CC delta T C, and that's going to be equal to minus MA CA delta T A. Okay, there we go. Now, within delta TC and within delta TA is T final. So we're going to have to expand that just like we did a second ago when we were doing the aluminum block. Okay, so we're looking at MCCC T final minus TC initial, and that's going to be minus MA CA T final minus TA initial. Okay, just like this. Okay, and sort of kind of stepping back from things, I know MC, I know CC, I know MA, I know CA, I know TCI, I know TA. The only thing I don't know here is T finals. All right, and there's only one of those, so I got one unknown in my one equation. So one unknown, one equation, we can solve this thing. All right, so let's get after it. And so we're going to have here MCCCTF minus MCCCTCI. It's going to be minus MACAT final plus, because it's minus times minus when we put it in there, MACATAI. Okay, now let's put all the TFs on one side of our equal sign. So we're going to have MCCCTF plus MACATF, and that's going to be equal to minus, just kidding. Okay, it's going to be equal to MCCCTC plus MACATA. All right, and those should be initial thingies there. Okay, just like that. Okie dokie. Now, if I take my MC terms to the other side and my MA terms, anyway, I'm going to do a couple of steps at once, but I think you'll be able to follow here. What I need to do is extract this term and this term. Okay, so I'm going to end up with TF, and that's equal to MCCCTCI plus MACATAI, and divided by MCCC plus MACA, just like that. So that's what I've got for my final temperature there. Okay, just like that. Now we're ready to plug in some numbers. Okay, and this is going to continue to be kind of messy. Okay, but I'm confident we can handle it. So TF then becomes, okay, I'm going to do the denominator part first. So I've got 250 grams times 0.386 joules per gram Kelvin plus 100 grams times 0.9 joules per gram Kelvin. And then on the top, I'm going to have 250 grams times 0.386 joules per gram Kelvin. Okay, times my TCI, which started at 400 Kelvin, plus MA, which is 100 grams, and CA, which is 0.9 joules per gram Kelvin, and TAI, which is 200 Kelvin. Ooh, baby. Okay, check that action out. Okay, so now let's look at our units real quick, see what we got. We'll start in the denominator. I've got grams canceling grams. So this term over here is really joules per Kelvin. Grams canceling grams. I got another joules per Kelvin. So that's nice. They need to match since we're adding them up. Then we're going to have grams. Grams, that's good. Kelvin, Kelvin, that's good. We're left with joules up here. Okay, and grams, grams, kelvins, kelvins. Again, we're left with joules. Okay, so then my joules in the denominator cancels with the top, and we're left just with kelvins, just like that. Okay, and so, yeah, anyway, when we run the numbers on that thing, it's going to be like 305 or something like that. Let me see if I can get that calculated for you. Hang on. Okay, yeah. So I just ran the numbers there on my calculator so I could get you an answer. If I can make it a little bit, tiny bit smaller, I need just a little scotch more room. Anyway, what we get then for T final is 30. Cried, what was it? 303 Kelvin. There we go. Okay. All right, there we go. And so that kind of an approach is really useful for a wide variety of situations. Okay. Trying to find what was the initial temperature of one object, maybe try to find what was the specific heat of one of the objects. Okay, anyway, just a large variety of things we can do with that one. Okay, there you go.